Hello everyone, welcome to my YouTube channel. In our last video, we were discussing about the definition of linear sum of two subspaces or more subspaces. Today we will discuss the dimension of the vector space, but before that we need to discuss about the finite dimensional vector space and infinite dimensional vector space. So definition of finite dimensional vector space is as follows. A vector space V over F is said to be finitely generated vector space if there exists a finite subset S of V such that V can be written as the linear span of the S. That is, each element of the vector space V can be expressed as the linear combination of elements of S. This S is nothing but the basis of the vector space V. So in short, you can say that S is basis of the vector space V, and the number of elements in the vector space, number of elements in the set S is said to be the dimension of the vector space V. And if the number of elements in this set S is finite, we say that this is a finite dimensional vector space. Now move to the definition of the infinite dimensional vector space. A vector space which is not finite dimensional is referred as infinite dimensional vector space. That is, if there does not exist any finite subset S such that each element of V can be expressed as the linear span of the set S, then we say that this vector space is of infinite dimension. So let's take some examples of infinite and finite dimensional vector space. So our first vector is vector spaces Rn over R. This is the set of n vectors. So the basis for this vector space is E1 equals to 1, 0, 0 and so on 0. E2 equal to, this time we will take the unity at the second place, 0 and so on 0. Proceeding in this manner, we get En equal to 0, 0, 0 and so on 1. So there are n elements which are here in the set S. So these are the elements of the set S. So this set S, if the elements of the set can span the whole vector space V, then we say that the number of elements in this set is said to be the dimension of the given vector space. But before that, we need to check. As you can see, this is a standard basis, so that this must be Li. S is Li, and each element of the vector space for all V belongs to capital V. This V can be written as the linear combination of the elements of S, that is A1 E1, A2 plus A2 E2 and so on An En, where A1 A2 and so on An are coming from the field R. So you can see that each element of the vector space V can be expressed as the linear combination of elements of S. So we can say that S forms a basis for the vector space V, and the number of elements in the basis is called the dimension of the vector space. So the dimension for this vector space will be, how many elements are there? N elements, E1, E2, E3 and so on En. So dimension of V becomes N. So I hope the definition of the dimension is clear. So in short, we can say that the dimension of the vector space of V over F is equals to number of elements in the basis of V. In the basis of V. Our second vector space is Mn cross n over R. This is nothing but the collection of or vector space of all n cross n matrices whose entries are coming from R. Now it's hard to find the basis of n cross n matrix, so because we don't know about the value of n. If the value of n is large, we have to take so much space to form the n cross n matrix. So if I take n as 2, then V becomes m2 cross 2 over R. In this case, it's easy to find the subset of this vector space V. So if I take a set as 1 0 0 1 comma, sorry, this is 0. At first place we are taking unity and other places are 0. In the second case we take at the second place as unity and other places 0. Similarly, this becomes 0 0 1 0 0 0 0 1. So this is the subset of the vector space V. Now we need to check that is it a basis. If it is a basis, the number of elements in this set becomes the dimension for the vector space V. So let's check it out. Clearly you can see that this is linearly independent. So the set S is Li. Now we need to check that this can span the whole vector space V. So let an element A, B, C, D belongs to vector space V. Now if this element can be written as the linear combination of the elements of S, then we can say that this set S forms a basis for the vector space V. So let's check that can we write it or not. So A, B, C, D can be written as in the matrix form A of 1 0 0 1 0 plus B 0 1 0 0 plus C 0 0 1 0 plus D 0 0 0 1. So you can see that I have chosen an arbitrary element of the vector space V, and I am able to write the elements of the vector space V in the linear combination of the elements of S, where A, B, C, D are coming from the field R. This implies that V can be expressed as linear span of S. So I can write V is equals to linear span of S. So this represents that this S forms a basis for the vector space V, and this is called standard basis. Today I will discuss just a standard basis and some other examples. So this is standard basis for this vector space, and the number of elements in this vector space are 1, 2, 3 and 4. So the dimension of the vector space becomes 4. That is, dimension of M2 cross 2 over R is equals to 2 square, that is 4. So in general, the dimension of N cross N over R can be written as N square. So that will be the dimension. Dimension of N cross N over R is equals to N square. Now let's take our next vector space. Now our third example is V is equals to Pn over R. This is nothing but the vector space of all polynomials with real coefficients. So if I write, then I can write it as, since here n is given, so there must be n, the degree of the polynomial must be n. So this type of element will be there, a0 plus a1x plus a2x square plus and so on plus an x to the power n, such that all the ai's belongs to the R, where I runs from 1 to n. Now if you see, each and every element can be written with the help of these vectors x, x square and so on, x power n. So the set S will be of form 1 x, x square and so on, x to the power n, and this forms a basis for this vector space V. Now if we see the number of elements in this set, these are n elements and this one element, together this can form the dimension of V. This can form the basis for the vector space V, and number of elements in this set is n plus 1. So dimension of V becomes n plus 1. Now let's take some examples of those vector space in which we will not take standard basis. These are the standard basis for these vector spaces. But now I am going to take some more examples in which I will take those bases which are not standard. Now we have a vector space V is equals to R cube over R, in which a subspace is given. W is equals to x, y, z, that is a triad belonging to R cube, such that x plus y equal to 0. In this case, we have given a subspace which is consist of all the triads belonging to R cube, but one condition is also given. In that case, we apply a formula, that is a short trick that we use to find the dimension of the vector subspace. That short trick is that let V be a vector space, V be a vector space over F, and W is the subspace of V. Subspace of V. Then dimension of W. Here dimension of V is what? 3. Dimension of V is 3. Because if you write the standard basis for this vector space, that will be 1 0 0 0 1 0 and 0 0 1. So 3 elements are there in the basis of vector space V, so dimension of V becomes 3. Now if we try to find the basis for the vector space W, in that case we use this formula, that dimension of W is equals to dimension of V minus number of Li conditions. Li conditions. So if you see this, there are 3 variables. So dimension of V is 3, and number of Li condition in this vector subspace is 1. So dimension for this vector subspace becomes 3 minus 1, that is 2. That is dimension of W is what? 2. Dimension of W can also be determined by this formula, that number of linearly independent vectors or variables. These determines the dimension of the subspace W. Because if we use this condition x plus y equal to 0, x plus y equal to 0 is given, then we can write y as minus x. So the subspace takes the form W is equals to, we will put at the place of y minus x, then this becomes x comma minus x comma z belongs to R cube, such that x comma z are coming from R. So there were 3 variables at the start, but after applying this linearly independent condition, we have only 2 variables, 2 independent variables. So the dimension of W will be 2. So this is also a method to find the dimension. So I hope the definition of dimension is clear to all of you. There is one more example that is left. V is equals to C over R. what is the basis for this vector space? Before that, we need to define this vector space V. This is the set of all, this is vector space of complex numbers whose entries are coming from R. So this is nothing but it will be of type A plus IB, such that A comma B are coming from R. So if I can write it as 1 dot A plus iota dot B. So what are the elements that can generate the whole vector space? Clearly you can see this is nothing but 1 comma I. 1 comma I are sufficient to generate the whole vector space. So this must work as a basis for this vector space V, and they are linearly independent also. So number of elements in the basis for the vectors in the basis of the vector space is 2. So dimension for this vector space is 2. So I hope that the definition of dimension and its examples are clear to all of you. And if you are liking my content, please subscribe my channel. Thank you.